Okay, so we have seen some of the thyristor based rectifier circuits, right? In this video, we are going to talk about a concept which is known as commutation overlap. So, if you see the word commutation in context to rectifier circuits, in context to thyristor rectifier circuits, is it essentially means the transfer of current from one device to other, right? So essentially from a thyristor to diode, or diode to thyristor, or some other device to some other device, right? So the word commutation essentially here means the transfer of current from one device to another device. And in fact, that is the reason that these converters which we have seen till now, which are the diode rectifiers and the thyristor rectifiers, they are also known as line commuted converters or rectifiers. Why is that? Because if you see, a thyristor turns on based on the gate, but it turns off because of the input sinusoidal voltage, right? When the voltage polarity changes, thyristor turns off and so on. So therefore, the commutation process, commutated converters, right? So the commutation process is driven by the line or by the source, right? And that is the reason these converters are also known as line commutated converters. Right. So now the process of commutation, what we have seen till now, for example, let's take the case of full bridge, fully controlled single phase SCR based rectifier, right? Let's take that case. If you see, this was the circuit. Let's assume load which is highly inductive for the time being. Current is I0, and this was connected to source, right? Now in this case, when the current, let's say, is flowing through T1, and then it wants to, let me number it, T1, T2, T3, T4, right? So let's say T1, T2 are conducting. That means current is flowing in this direction, right? And when suddenly T1, T2 are stopped conducting, and T1, T3, T3, T4 starts conducting, in that case, the current in the input side, instead of flowing like this, it would just suddenly start flowing back because T4 will start conducting, right? So if you see the input current, if we have drawn this also, input current could be like a square wave kind of thing, right? Depending on which devices are conducting and so on. So it could be have a sudden change in the input current. The output current remains constant, but the input current, as we have drawn till now, we have drawn a steep change, right? Depending on when T1, T2 transitions to T3, T4. Now this thing is okay if it is an ideal source, right? So till now we have talked about an ideal source. But in real source, this is not possible, because if you see a real AC source, it would also have some amount of inductance associated with it, right? So there is a phase and a neutral line. Now this line might be coming from a distribution transformer. The distribution transformer may also have some series impedance plus the line impedances. So total it will have some series inductances L1 and L2. Now, as we understand, a current through an inductor cannot change instantaneously. Why? Because that would require infinite voltage to be developed. Therefore, the transition of current, which in this figure we are seeing instantaneous, does not happen in case of a practical supply or a practical AC source. Right? So, what essentially means is this transition between the current, or the transition between the current flowing from T1 to T3, right, does not happen instantaneously. It takes some finite time wherein current slowly reduces in T1 and then also slowly increases in T3. So that is called as the commutation overlap. Commutation overlap is essentially the period, we would represent it by mu, is essentially the period in which both the thyristors, let's say if we talk about T1, T3, then both T1, T3 are conducting and current is reducing in one and increasing in the other one, right? And that period is called as commutation overlap. In an ideal source, commutation overlap would be almost zero, so mu would be equal to 0. But in a practical source, the value of mu depends on the inductance values L1 and L2. So now what we'll do is we'll continue maybe with the same example of a fully controlled thyristor rectifier, and we will try to calculate the value of mu. We'll also see whether this commutation overlap has any effect on the output voltage and so on. So let me redraw the circuit, excuse me, and let us then try to derive these expressions. Right, so let's say this is and let's say I club both L1 and L2 and show it by an L effective, right, which is essentially the total inductance which would affect this transition. Right, so L effective is the total inductance. These are the thyristors T1, T2, T3 and T4. Now what happens is in our, let me draw the waveforms. So this was T1 where I'm giving pulse to T1 and T2, and this is, let's say, where I'm giving pulse to T3 and T4. Right, now in earlier case, let me also draw the input current. Now what happens to the output voltage when T1, T2 gets triggered? Ideally the output voltage should go like this and go like this, and then again on the top and then again on the bottom, right, something like this. But now here what happens is when you turn on, and what should happen to the current? Ideally current should be negative, right, because T3, T4 are conducting, and at this point current should suddenly become positive from the input side. But that does not happen. So instead what happens is you have a period, so at this angle, till this angle current is negative, and then you have a period in which current will slowly rise up and become positive, right? So this is the period, because current cannot change instantaneously from the input side. So this is the period, we call it as commutation overlap, and we represent in terms of radians by mu. So mu is expressed not in terms of time but in terms of radians. You can very well express it in terms of time also, right, that what is the commutation overlap period. You can define it in terms of time, you can define it in terms of angle. Here in this figure I'm defining in terms of angle. So what is happening in this mu period? So earlier T3, T4 were conducting, right? Now you have given pulse to T1 and T2. The current was flowing through T3, right, the full load current IO. Now full load current IO should flow from T1, but this transition is not instantaneous, so it takes some time. So for some duration, you see both T1 and T3 are conducting, right? Both T1 and T3 are conducting. Why? Because T3 current is reducing. So if I plot currents, let's say this is IT3. So IT3 is reducing and IT1 is increasing. But in this period, both T1 and T3 are conducting. Similarly, if you see the bottom, same thing, both T2 and T4 would conduct for this short period mu. So what is the equivalent circuit diagram in this period? You have a source, you have an inductance, L effective, and all the four devices are conducting. So essentially, this potential is 0, right? And this is your output current source. So if you see in this period during mu, all the 4 devices are conducting and your output voltage is nothing but 0. Why? Because T1, T2, T3, T4 all are conducting. So you can see that, just see the KVL, you will see that the output voltage is 0. So therefore this red one, the output voltage actually looks something like this. So it remains negative, right? It's a full bridge converter, it remains negative, then it keeps 0 for mu period, right? And then it actually follows this waveform. Then again it goes negative, remains 0 for some time, and then again follows this period. So this is how the output voltage looks like in case of commutation overlap in this particular circuit topology, right? So I would suggest that if you are looking at some other circuit topology, do not blindly use the formulas or the derivation that we are doing it here, right? See the basic principle, try to identify the path of current, try to see during this computation what is going to be the output voltage, and then accordingly you can decide upon the output voltage waveform, right? Okay, so far so good. Now we have sort of understood it qualitatively, what is happening. Current is slowly going down, input current is slowly building up to positive sign, right? So we have understood qualitatively during this period the output voltage is 0. But now let's also write some equations and try to have an expression for, let's say, mu, right? So let's try to derive an expression for mu to begin with. So how do we find mu? So if you want to find mu, you can write the Kirchhoff's voltage equation during this overlap period, right? So what is Kirchhoff's voltage equation during this period? Vin is equal to L effective into di by dt, right? You can take dt here, so you can say Vin dt is equal to L effective di. You can integrate starting from, so in this case you can what is this point? This point theta is equal to alpha firing angle to this point. This second point is theta is equal to alpha plus mu. And what about current? On left side the input current is nothing but equal to minus IO, and at the end of this computation period it will become equal to plus IO. Right? So here we have an integral wherein you are writing Kirchhoff's voltage law and then integrating it over a period of mu. Okay, now let's see what happens. We can solve it. We can write Vin is nothing but Vm sine of theta d theta upon omega going from alpha to alpha plus mu is equal to L effective into 2I0. Can further rewrite it as Vm by omega to cos of alpha minus cos of alpha plus mu L effective into 2I0. Keep this equation in mind. Let's call it equation number 1. We'll be using it again. But as of now, let's also continue with this equation. So Vm by omega cos A minus cos B is minus 2 times of sine of A plus B by 2 into sine of A minus B by 2. Right, now if you want to have an approximate value of mu, right, you can assume that mu is much smaller than alpha, right? So therefore you can write this thing as Vm by omega into 2 into sine of alpha into sine of mu by 2. You can almost write it as mu by 2 L effective. Right. So in this case you can, if you want to find the approximate value of mu, which would be in radians per second. right, which is obviously a function of L effective. It's also a function of output current, input voltage Vm, and the frequency omega, and the angle at which you are firing alpha. Right? It's a function of all of these variables, but you can find the value of mu. Alright, now once you have got the value of mu, you understand what is the period in which this commutation would happen. Now the next step would be to find the average output voltage, because you see, if it would have been an ideal source, the average output voltage would have been different. We know the expression, it's 2Vm by pi cos of alpha. But now we have some period, if you see the period mu, where the output voltage is actually 0. In earlier case, it was supposed to be V in. So therefore, the output voltage would certainly change average value. And as it is seen from this figure, the average output voltage will actually reduce as compared to an ideal scenario. So let us try to find this new average output voltage. Let me use this space here. So the average output voltage is, I can write it as, if you see the figure, if you see, focus on the red waveform, which is VO, I can write it as the original average output voltage, which was the average wherein the voltage would have increased at this point itself, at alpha itself, which was 2Vm by pi into cos of alpha, minus the average value, which is 1 upon pi integral of alpha to alpha plus mu Vm sine theta d theta. Why? Because this part is actually not present in the new voltage. So therefore the old average voltage minus this part which is not present in the new voltage would give you the new average. So now let us try to solve it. So we can rewrite it as 2Vm by pi cos of alpha minus Vm by pi cos of alpha minus cos of alpha plus mu. Right? Now if you see equation 1, we can substitute this term from equation 1, and therefore what we'll have is 2Vm by pi cos of alpha minus omega L effective 2I naught upon pi. Okay, this is going to be your new average voltage. Obviously, as we expected, average voltage is less than the average that you would have got if this would have been an ideal source. And this difference, the drop in the average voltage, is proportional to the inductance, effective inductance is proportional to the output current and frequency. So with these basic principles, you can apply the, you can try to find the average output voltage for some of the other circuits that we have discussed in previous lectures. For example, you can talk about, let's say, half wave kind of thyristor rectifiers. You can try to calculate, right, where there's a freewheeling diode, or you can consider some other circuit, for example, a half control rectifier. Right, you can talk about a fully controlled rectified with a freewheeling diode and so on. So you can apply these basic principles to any of the circuit and can calculate the average output voltage and the commutation angle mu.